Thank you to the organisers for the invitation and this speaking slot, and also thank you for giving me a not so inconvenient time. Living in Australia, it's always, you end up with kind of tricky times for these kind of talks. This is variously joint work with Oliver Junger from TU Munich, Peter Koltai from Free University Berlin, Narrative Santi-Tistikorn from Surrey, and Martin Stahn from Potsdam. And as I was saying in the pre-discussion, so I'm from Dynamical Systems. I won't assume any background in dynamical systems for this talk, so I'll try to build up things as I go. So one of the first aims is to briefly show you how nonlinear semigroups arise naturally in nonlinear dynamical systems, where the single parameter is time. And then I want to move on to building a family of linear operator semigroups, and these are going to be called transfer operator semigroups. And they describe the evolution of mass distributions under the dynamical system. And then most of the talk is demonstrating how these transfer operator semigroups can be used to analyze and manipulate transport and mixing of the nonlinear dynamical systems. So there's two main parts to my talk. So in the first part, I want to describe how the spectrum and the eigenfunctions of these semigroups can tell you about the transport structure of the dynamics. And in the second part, I want to discuss about how these are really convenient frameworks for setting up optimization problems to manipulate the system to enhance or diminish mixing. So, okay, the setting is you have some domain, and I want to keep things simple today. So let's just say it's a compact subset of RD. Sometimes I'm going to consider things like flat tori, flat cylinders, etc. And you're going to have a family of diffeomorphisms, phi. They're parameterized by the single parameter t, which we think of as time, and they're going to satisfy a semigroup property. So given an initial point in your domain, you think of phi tx as the position in your domain where the point ends up after flowing for time t. And as t increases, it traces out a path, a trajectory, an orbit, initialized at x, and evolved for t units of time by our dynamical system. So we call this phi t a flow map for our system. So the easiest way to generate one of these things is by integrating a vector field. So what I'm showing you here is a 2D domain. In fact, it's a flat cylinder, so the left and right-hand edges are identified, and so the horizontal direction is periodic. And yeah, the vectors indicate the vector field. And if you want to make one of these trajectories like the black curve, then this is just an integral curve for your vector field. So the vectors are always tangent to the curve. And if you initialize a particle, say here, then as you flow, it moves along the trajectory like this. And so we say that the flow map phi t solves the ODE, x dot is Vx, and the flow map satisfies ddt of phi t is V. Okay. So now I don't want to think about the evolution of individual points as I was just describing, but rather I want to put some density or distribution of points over my domain, and I want to evolve that. So I think of some density f in say L1, and I want to define a linear operator that is going to represent the natural push forward of this function by the dynamics. So let's say you have initially at time 0, you have an ensemble distributed like f. Then at time t, this is going to be distributed by ptf. And in this setting where everything is just driven by phi, you have an explicit expression for this linear operator. It's essentially a composition operator. So you're composing with the inverse of phi. And you have this additional scalar normalization term, and that is merely there to ensure that when you push forward a density, so some distribution with integral 1, that it remains a density. So this is just a normalization factor. Essentially, it's a composition operator. Now, this is not too hard to show that this family consists of Markov operators. So that means they're positive operators. They preserve integrals where Lebesgue integration is met, and they're contractions in L1. And they, of course, satisfy semigroup properties. So if you push for time t, and then you push for time s, that's the same as pushing for time s plus t. Now, the spectrum of this operator is going to be the key tool in this talk, but I'm not going to work directly with the deterministic phi. The reason is that if you want an informative spectrum, then you have to restrict the class of phi to things like phi that are locally uniformly expanding in your domain, or at every point you have designated directions of expansion and contraction uniformly. So that's the hyperbolic setting. And then you can construct exotic Banach spaces on which your operator is quasi-compact. So if you're interested in that sort of thing, there's a lot of work on that by Vivian Baladi, Faurer, Calangelo Liverani, and their colleagues. So today I want to keep the class of dynamical systems general and the Banach spaces standard, so things like L1, L2. And instead I'm going to consider the SDE, where I have my, my velocity field as before, but I add some noise, some Brownian motion. And I'm thinking of epsilon as being small. So now I can play the same game. I can say I want to have some ensemble of states F. I can define again my P in exactly the same way. The ensemble is distributed like F at time 0, and PTF is going to be the distribution at the later time T. And now you don't get such an explicit expression for this semigroup operator, but we'll see shortly that you get a nice expression for the generator of this operator semigroup. So again, sorry about the background noise. So again, we have that this family consists of Markov operators. So this is a copy of the slide I had before. So the addition of the Brownian motion doesn't change anything at all. And right, so we have this autonomous system. We have generating, this is giving us a one parameter semigroup. As usual, you have strong continuity at 0. You can take a derivative to form your infinitesimal generator in the usual way. And you have, which is going to be important for us later, you have the standard kind of spectral mapping theorem, where you can map from the spectrum of your semigroup to the exponentiation of the spectrum of your generator. And so intuitively, you think in the usual way that the semigroup is generated by exponentiating the generator. Now coming back to the transfer operators, if you have your ODE, then the generator that you get is minus divergence of this distribution F times V, the velocity field. If you have this the Brownian motion version, then you additionally get a diffusion term, so you have a Laplace. But yeah, otherwise it is the same. So mostly we're going to be dealing with this second expression. Now, what does it mean for this SDE to be mixing? So there are various answers to that, but the one I'm going to use is going to be based on the spectrum. So we have our generator. The right-hand side is often also written as partial df dt. So what this means is you fix a point in your phase space and you ask, how is my distribution changing at that fixed point in time? Now, if there is no change, if that change is 0, then you found a function, so GF is 0, and what you found then is what's called an equilibrium density of your SDE. So you found a very special distribution so that when you evolve according to the dynamics, there's no change. So you're at equilibrium. Now the rest of the spectrum is contained strictly in the left half of the complex plane. That's because we have the semigroup is a contraction, and we're taking logs here. So the decay is going to be controlled as usual by the real part of the eigenvalues. So the more negative, the faster decay. And because of the mass conservation of our flow, or equivalently, I'm putting non-boundary conditions on this PE here. All the eigenfunctions that correspond to eigenvalues that are not 0, they all have 0 mean. So they're all having Lebesgue integral 0. So they're signed. They have positive and negative values. And in particular, the eigenvalue lambda 2, this is what is going to determine our slowest mixing rate for our SDE. So I look for the eigenvalue that has the largest non-zero real part. So I'll come back to the example flow I had at the start. It's a bit hard to tell from the vector field, but this is an area preserving flow. So the constant function is preserved under the action of the flow. And what you're seeing on the right is a graph of the second eigenfunction for this stochastic DE. So red you can think of as, say, +1, and blue is -1. And one way to think about this is if you want to distribute mass over the domain in such a way that signed mass equilibrates as slow as possible, then this is the distribution that you should make. And the reason, I mean, the intuitive reason, if you look at what is going on here, you have this central jet that is moving left to right around the cylinder, and everything above that, at least for the deterministic flow, everything above that is stuck above this black trajectory. So by uniqueness of solutions of ODEs, it's not possible for two trajectories to cross. And so everything that begins in this loop here has to stay in the loop. Everything that begins above this curve has to stay above this curve. Everything in between these two lines has to stay there. Everything that starts here stays there, and everything that starts here stays below this line. So at a macro scale, you essentially split the cylinder into top and bottom, and you put negative mass at the top, positive mass at the bottom, and that's going to equilibrate the slowest. So that's essentially everything I've said here. Now, as I indicated, there are 5 pieces. There's this piece here, the piece in the loop, this piece through the middle, this piece, and this piece. And if you compute the top 5 eigenvectors of the generator, then you get what you see in the top row. Now the first one is really constant. The color scale here is extremely narrow, so it looks non-constant, but trust me, it's really constant. This is the one that I just showed you, and here are the next 3. And if you look at where they're red and where they're blue, you can see, if you remember what that picture looked like, you can see that the red and the blue are picking out these 5 pieces, but in a kind of mixed up way. So what you can do is you can take this 5-dimensional eigenspace and rotate the eigenvectors to a new basis, a sparse basis, and that is what is done in the lower row. So the blue here is 0, and the red is 1. So this is a sparse basis, and what you get now is in every vector you just get one of these 5 pieces that I talked about before. So this can be done automatically using this sparse eigenbasis approximation algorithm. So now you've got these 5 pieces, you can just add them up, put them in one diagram, and this is what you get. And you can compare this now with the kind of classical analysis you might make using dynamical systems. So on the left-hand side, what we've done is we've found a hyperbolic equilibria, indicated by the dot here. And we found the connecting orbits that connect around the cylinder and come back. So there are two connecting orbits. And here's another hyperbolic point, and the trajectories of the two connecting orbits. And that would be the classical way that you would analyze the system. On the right, we don't know anything about the geometry. We just know the vector field. We construct our generator, and from the eigenfunctions, we can find these 5 pieces drawn from the leading 5-dimensional eigenbases. So this is the general idea that I want to discuss. We don't just have the slowest, but in this case we have the 5 slowest equilibrating pieces. You can make a connection with rates of escape from these pieces. So, for example, let's say you've got your generator, you have an eigenvalue lambda, and an eigenfunction f corresponding to lambda. What you can do is, similar to what I just talked about, you can define 2 sets, namely a plus and a minus, where this function is positive and negative. And you have this tight result relating the eigenvalue lambda to the escape rate from these 2 pieces. And in fact, lambda is equal to the sum of the escape rates from a plus and a minus. And what I mean by escape rate is you compute the conditional probability that you leave, in this case, a plus. So you're in a plus at time 0, and then you're leaving at time t, and you take the derivative of that with respect to t, and that's the rate at which you are escaping the set a plus. And yeah, so you have lambda as the sum of these 2 things. So if lambda is close to 0, then you have a slow escape rate. And that is why we're looking for these lambda that are close to the imaginary axis. If you have a complex lambda, then you have not just a fixed pair of sets, but in fact you have 2 cyclic families of sets that have low escape rate, and the rate is again given by the real part. So let me illustrate this cyclic idea with the Lorentz equations. So even if you're not in dynamical systems, you might have heard of or seen the Lorentz equations as one of the main examples of chaotic systems. So here's the Lorentz attractor, or at least a long trajectory sitting near the attractor. And it's well known that the Lorentz attractor is mixing. But what you can do is, if you want to find, if you want to put a complex distribution on the Lorentz attractor that mixes more slowly than would be suggested by the usual mixing rates, what you can do is basically extract a cycle around the wing. So this is a graph of the complex. You can think of this as the argument, if you like, the argument of the complex, a complex distribution on the Lorentz attractor. And if I can just pop out for a sec, so here's a movie, maybe it gives a better idea of what I'm talking about. So this is looping over one cycle length of the complex eigenfunction, and you see that you complete a complete loop. So there is the main cyclic behavior that you can extract from the Lorentz equations is this cycle length around the 2 wings. And you can actually, in the same paper that we talk about this, you can extend this. This is getting, I guess, less rigorous, but you can extend this to extracting other cycles like the El Nino Southern Oscillation cycle. So what we are doing here is working with sea surface temperature data, and we're trying to extract the ENSO cycle as the main cycle, again using a complex eigenvalue and using the complex eigenfunction to map what is a standard ENSO cycle. So maybe you're not familiar with this, but El Nino is where in the mid-Pacific, in the equatorial Pacific, you have this warm water of Peru. That means that it's usually pretty dry in Eastern Australia and wet in Peru. And as you move around the cycle, the water gets colder during La Nina, and the opposite kind of happens. It's rainy and cold in Australia and dry in Peru and upper North and South America. So we can find maps of this cycle using these ideas. So this motivates partly what I want to talk about in the rest of the talk, which is extending these ideas from autonomous dynamics to non-autonomous dynamics. So far we talked about x dot as v of x and noisy versions of that, and in many cases, particularly applications, you want to look at the vector fields that depend on time as well. So what I'm doing here is representing time as an additional variable, and I'm saying that the derivative of that additional variable with respect to time is 1. So like dt is 1. That variable just proceeds with velocity 1. Whereas here we had a flow phi t, now we have a flow that cares about where it starts. So it cares about the initial time t0, and then you are still flowing for some time t. Now, this situation is more complicated because there's no obvious candidate for a generator, and we have to work more directly with the semigroup, which cares about where it's going to start pushing from. And in general, it doesn't make sense, even if you work with the semigroup, it doesn't make sense to compute eigenvalues of this because your vector field may have some general aperiodic time dependence. And it also doesn't really make sense to compute eigenvalues of a spatial generator at a fixed time. So I'll discuss what doesn't make sense soon, and I'm going to focus mainly on periodic forcing because that's easier to set up and maybe also familiar for some people. Okay, so this motivates my next movie for 2 reasons. One is it's about periodic forcing, but also it's about trying to convince you that these things actually are real. So in the first frame, what you're doing is you're looking at a thin film of fluid. Okay, so you've got a very thin film of fluid. The camera is shooting down, and you've got some fluorescent dye on the left, the green, and the fluid has some salt in it, so it can be magnetically forced from below. And that forcing is periodic. And on the left, you just see what happens as the forcing goes. And on the right, there is a snapshot every period of the forcing. And now this is an incompressible fluid. So to this 2-dimensional approximation, it's area preserving. And so in the long run, you would expect the green dye to uniformly distribute over the square that you see. But this takes a long time. And at what you see at intermediate time scales is that a pattern emerges, a complicated pattern, and this complicated pattern you can think of this as convergence to F2, the second eigenfunction of our transfer operator semigroup. So the transfer operator is pushing. This is the action of the transfer operator pushing forward the distribution of green dye in the fluid, and the distribution that is most inhibiting the mixing is the one that you see, is the one that naturally appears in this simulation. So that's a nice real life expression of this behavior. Now there's a standard way, coming back to non-autonomous, there's a standard way in dynamics to turn a non-autonomous system into an autonomous one, and that's by augmenting with your time coordinate. So you make a new coordinate system where you simply adjoin time to your space. So you increase the dimension by 1 of your domain by 1. And this construction we had before, this is now written in terms of bold objects. So everything in this augmented space is going to be bold face. You can simply write this again now as an autonomous ODE. And this will generate an autonomous flow map, bold file. And we're going to make an autonomous semigroup and an autonomous generator. So let me discuss the periodic driving case. You've got your time on a circle of length tau. Your augmented process, as I mentioned, is autonomous. You have, you can construct in the usual way in this augmented space your transfer operator semigroup, and then you can build the generator from this semigroup, bold G. So bold G would act on a bold F. If you want to write this in breaking it down by time slice, so S is a time. So if you look at the S fiber of bold F, then what this bold G would do is you act on the S fiber with the S spatial generator, and you have to apply also the generator in time. But in time, it's simply a partial differentiation with respect to S, the time coordinate. If you want to write this back in terms of bold quantities, then you get something that's almost exactly the same as we had in the autonomous case. The only difference is that the diffusion is acting only in space. Okay, so we're not diffusing time. Time proceeds deterministically, so there's no time in the Laplace, but only space. But otherwise, this is looking almost the same as what we had in the purely autonomous case. Now, you can, using this, get a non-autonomous spectral mapping theorem. So this goes back to the theory of evolution semigroups. And so you have a result like the following. Maybe I'll start with B. So if you have an augmented eigenfunction of your augmented generator with eigenvalue bold lambda, then that is equivalent to taking the S fiber of F, pushing that forward from S around a full cycle with your operator semigroup, and what you'll pick up, you'll come back to where you began, and you'll pick up an eigenvalue e to the lambda tau. So if you can find such a collection Fs going the other way, you can put them together to make a bold F, and you would get this property. So these two are equivalent. Okay, so now we're ready to talk about optimization. And so again, we have either a steady or some time-dependent velocity field. This can either be an interval, or it could be tau S1. It could be a circle of length tau. Both are fine. The question I want to solve is, I have some velocity field. It has a certain mixing rate, as we've discussed, given by lambda 2. How can I make a small perturbation of that vector field so that I increase as much as possible the mixing rate? So I want to select from some small ball of radius delta in vector field space, some v dot, and then I want to choose the v dot so that the mixing rate of v plus v dot is greatest. So this is a very high level description of what I want to do. So a lot of people have worked on this problem. Actually, a lot of work is just simply on quantifying mixing rates. Most people are working directly at the nonlinear dynamic level. So they work directly with the vector field, and typically they do what I would call low parameter optimization. So they have a couple of small parameters that they're tweaking, and they want to tweak a couple of parameters to increase the mixing. And what we're doing here, I would say, is way, definitely in the high parameter regime, instead of just optimizing a small number of control knobs, what I want to do is compute a general perturbation of the entire vector field that most enhances mixing. Okay. And key to this is going to be transforming the nonlinear flow into our linear representation with the transfer operator and the generator. So, okay, let's set this up. So again, we have some compact domain. We have our space V of vector fields that we're going to select from. So they should be uniformly bounded, uniformly Lipschitz in space. I'm going to assume that at every time slice, the vector field is divergence free. This is not really necessary, but it just keeps a whole bunch of normalization quantities out of the expressions. We have again our Fokker-Planck equation. And this right-hand side is, you could write as the spatial generator at time t, acting on your F. And our solution operator is as before, and I just note that for positive t, this is compact. This is a compact operator in L2. Okay, now, because we're talking about periodically driven flows, it is appropriate to look at the eigenspectrum of pt tau. So you can start at any time, flow for a full cycle, and because you come back to where you begin, it does make sense to look at the eigenspectrum. If you have a fixed point of this operator, then that's going to be, that's interpretable as a time-dependent equilibrium for the system. Although, because we've assumed divergence freeness, this is going to be a constant function for all t. And yeah, by flow K theory, the second, in fact, all the isolated eigenvalues are going to be independent of t. So it doesn't matter which t you start at, you're always going to get the same lambda. This is related to the spectral mapping theorem here, where the lambda that you see here doesn't depend on s. Okay, it's independent of where you start. Okay, and so what is important for us is the dependence of lambda on v, on the vector field, because I'm going to change this and I want to see how my lambda is changing. So in order to talk about differentiability of lambda, we have a norm on our class V of vector fields. So we'll set this norm to be the max of the sup norm, and it's Lipschitz in space constant. So this sup plus regularity is a fairly standard kind of norm that you would consider. And with this, you can show that the map from V to lambda of V is Fréchet differentiable. So this is in a recent paper by Koltai and Plonker using earlier work of Rosenblum and Klöckner. And yeah, in what follows, it's going to be advantageous to work with the augmented generator on our augmented space. So that's why I mentioned it. So the strategy we take in the paper here is to piggyback off the differentiability of lambda for the semigroup. So back here we have that this map is Fréchet differentiable. This is where lambda is computed using the semigroup P. And what I really want is differentiability for the generator, but I'm going to get this using the spectral mapping theorem. All the eigenvalues are isolated and there's no problem. So this differentiability carries over to bold lambda for the generator G. So this eigenvalue bold lambda is going to determine our mixing rate. And so the aim then is going to be to increase the mixing rate by perturbing the vector field V so that we push the eigenvalues of bold G more to the left on the imaginary axis. So mathematically, what we want to do is minimize this Gatto derivative You want to look at dd lambda of lambda delta, where lambda delta is the lambda you would get from the generator corresponding to V plus delta times V. And fortunately, this has a very simple expression. It's simply the inner product of the eigenfunctions corresponding to lambda. So G naught here is, well, let me say H naught, oops. H naught is the eigenfunction of G, and G naught is the eigenfunction of the adjoint of G, both corresponding to lambda. The E here is the perturbation, so this is the G dot. And in our particular setting, because we're changing just the V, this has an explicit expression, namely gradient of V dot times F rather than V times F. So all this is in principle known. And so the strategy in pictures is going to go like this. We have some original vector field. We approximate our generator. We do the optimization on our generator, and then we infer back from the new generator the optimized velocity field. So we pass to linear space and linear objects, do the optimization there, and then pass back to the nonlinear objects. And yeah, if your spectrum is looking like this, this is the imaginary axis. You want to push everything to the left. So there are two strategies that we used. Briefly, the first one is where you discretize the phase space and you make a discrete generator. So N is the order of the discretization. For the particular discretization we used, this is some large sparse matrix. It's large, but we only want a small number of eigenvalues near the imaginary axis because these are the ones that we want to move. And then we perturb this discrete generator so as to increase the gap as much as we can, subject to constraints on the size of the perturbation. And the nice thing is that with this particular construction, the objective and all the constraints you can write as linear constraints. So you have linear objective, linear constraints, and the whole thing can be set up as a linear program. This is the entire linear program. I don't want you to read anything here. I just want to show you that it's enough to, it's simple enough to fit on one slide. Okay. So let's look at some examples. So here is a very simple example where the vector field is just a single gyre. So trajectories are concentric circles. And because trajectories are concentric circles, the main obstacle to mixing is how you get from the center to the outside of the domain. So here's I initialize with the vertical strip, and the vertical strip is evolved by the flow, and you can see how the vertical strip is getting mixed. So we compute the discrete generator. This is what the spectrum numerically looks like. And these are the first 6 eigenfunctions. And if you think back to what I was saying earlier about the extreme positive and negative values being important, you see you have extreme negative values at the boundary, extreme positive ones in the center. And so this is reflecting the fact that you want to somehow get from the center to the boundary and vice versa. So this is the problematic, this is the obstacle to global mixing. So this is the result of the optimization. The blue is the original, the red is the optimized, and this is a small perturbation. So I put constraints on it, like the speed cannot increase. I put the sup norm difference cannot be larger than a certain amount. The sup norm difference of the first derivative cannot be larger than a certain amount. All these kind of constraints you can put on it. And so the gap has been slightly increased here. So from 0.07 to 0.09. And on the left, you've got the original. On the right, you have the optimized version. And if there's anything wrong with what is happening on the left, it's that near the center, the spacing of the curves is larger. So you have this non-uniform space, and you have big gaps here, but smaller near the boundary. The one on the right, it's much more equally spaced. So you put more effort into twisting more tightly toward the center, and this is going to lead to more rapid mixing. So that looks okay. That's a fairly simple example. Here is a periodically driven example. The evolution of a blob is, as you see here, there are parts of the phase space that are not easily accessible around here and around here on the right. And it's not so easy to get from the left half of the domain to the right half of the domain. So these are the main two obstacles. This is just a picture of how the periodic forcing works. So you have this separatrix in the middle and two circular gyres on each side. And after a quarter period, that separatrix moves to the right. At half the period, it moves back to the center, and at 3/4, it goes up to the left, and then it will go back to the right. So you have this oscillating separatrix, and this is what's generating the complicated behavior. So again, we do the same procedure. The gap here in the spectrum has been about doubled. The blue is the original, the red is the optimized. So again, I'm not making a huge perturbation here. Now, yeah, I guess this is for dynamical systems people in the audience. So what you're looking at here is many, many trajectories, and I'm looking at what happens on a particular time slice around the cycle, around the forcing cycle. So this is a Poincare map. And while generally speaking, where you see this kind of fuzzy, unstructured set of points, that's where you have good mixing. And where you see this structure, that's where you have poor mixing. And so this is the original and this is the optimized. And so in the optimized, you greatly increase this well-mixed part of the domain. And this is a pretty well understood dynamical system as well. So in the 90s, the exchange of fluid from the left to the right half was explained through what's called load dynamics. So it's the area in these regions here that controls how much fluid can pass from the left to the right in one cycle of the driving. And what you see in the optimized version is that the area of these pieces here is greatly increased. So what I'm trying to describe on this slide is that if you just see what happened from this operator optimization, if you see what happened geometrically, it makes a lot of sense. On the other, it would not be obvious how to, if I told you, please make the lobes bigger, it would not be obvious how to do that. So passing to this linear representation seems to produce, after the fact, we can look at what happened and we can say, well, actually it did something really interesting from a geometric point of view. And here are the two simulations. So this is the original, this is the optimized. And as you watch this, you'll see that more of the interior regions around here are accessed more quickly in the optimized flow. And also that you more rapidly exchange fluid from the left to the right in the optimized flow. So by making these small changes, you can make, with more time, several periods, you can make dramatic changes to the amount of mixing that occurs. I just have, I guess I'm, Chair, please tell me if I'm running out of time. But
I think you have still 5 minutes.
Okay, that's good, thank you. So just briefly, the alternative strategy that we looked at was the same kind of setup, where you have, again, you want to minimize this Gatto derivative, and now instead of discretizing the domain, we instead don't discretize the domain, but rather discretize the function space of the perturbations. So we take a dictionary, we create a finite dictionary of perturbations that we might want to make. And what we're going to do is select a linear combination from that dictionary. So this would be some large dictionary of vector field perturbations. They're spanning some perturbation space C. And so now we want to minimize our objective from up here, subject to selecting something from our perturbation space C and with unit norm. So with this construction, what you can do is prove that a unique optimum exists, which is very nice. So there is an optimum and it's unique. And so we're already in a very nice position. And because it turns out that, well, because the objective is linear and the constraints are either linear or because of this Sobolev norm here, I think we used we only ended up with quadratic type constraints arising from this. So it was not too difficult to apply Lagrange multipliers, and then you can obtain really an explicit formula for this unique optimal perturbation. Okay, so this is in this paper, and this is my second last slide. So this is a similar kind of system to the one I was showing you before, just with a different viewpoint. So this is what's called a stream function. So what I've done is taken a snapshot of my vector field, and then with that fixed vector field, I make trajectories. And these are the streamlines that you see. This is a stream function of the optimal perturbation. And when you add this to this, then you get your perturbed a stream function for your perturbed flow. So again, not too different from this one. If you seed with two blobs of fluid, this is the evolution after 4 time units with the original map, and this is the evolution after 4 time units with the perturbed map. So even though the underlying stream function representation is not too different, you can get already after just 4 time units a significant change to the I mean, arguably, I think this is mixing better than this is. Okay, so that is it. I guess the 3 main points I want to make are that these semi-groups of transfer operators are powerful linear analysis tools to study transport and mixing in nonlinear dynamical systems. I think this is a point that's been made by several talks in this conference. The spectrum and the eigenfunctions of these semi-groups and the generators tell you about the slow decaying distributions in the phase space. And so this is just what we want if we want to do some manipulation by optimization. And in fact, these linearization methodologies through linear operators provide a very convenient framework for doing this if we want to perturb so to enhance or diminish mixing or to make some other kind of change to the transport properties of the flow. And yeah, these are the references for the papers I mentioned, and I will stop there, and thank you very much for listening.
Okay, so thank you very much for the talk, for the nice talk. Yeah, now we have time for discussions and questions. So please go ahead if you have a question.
I have a question.
Okay.
I'm very impressed by this talk. Can you please tell me, are there some studies of that sort dedicated to the Navier-Stokes equation?
I don't know. I'm not a Navier-Stokes person. So you mean the optimization?
No, I mean, is it possible to rewrite the Navier-Stokes nonlinear equation as a linear equation in infinite dimensional setting?
So you want to write? Well, I mean, this is already the Navier-Stokes is a nonlinear PDE, and so what I was talking about is so the ODE or the SDE, you can write that when you take this to the level of ensembles, you can write this as a linear PDE. So all the PDEs that I talked about, well, there was only one of them, the Fokker-Planck equation. So this is a linear PDE. Yeah, with Navier-Stokes, I think it's going to be harder because you already begin with something that's infinite dimensional and nonlinear, and now you need to lift that you need to linearize that somehow. I don't off the top of my head know of people doing that, but I guess in principle, one could try to do that. Yeah.
Maybe we can do it together.
Maybe.
And then approximate this.
Yeah.
And then we can approximate this linear semi-group with the Chernoff approximations.
Mm-hmm. Okay, sounds very interesting.
I will write the letter.
Thank you.
May I ask a question too?
Yes, of course.
Yes. So in your first numerical method, you have this video at the end of the optimized and the non-optimized flow with a mixing between the left and the right.
This one?
I think it was. Yes, thank you. I'm not sure I got this right. So is this now just the transport process, or is there also diffusion with the Brownian motion?
No, this is yeah. So so in the computation there was some in the operator optimization there was some diffusion, but what I'm showing you here is just pure advection. So I guess I'm always working in this regime where the epsilon is very small, and so I switch back and forth between having some small diffusion and having no diffusion. So this is illustrating what happens with no diffusion.
And is there? Can we say that the optimum does not depend on epsilon?
I think probably not, because as you shrink epsilon, it depends on the system. As you shrink epsilon, it could be that finer and finer resolution obstacles appear. It would depend on your dynamics. So I think probably as you shrink epsilon, in general, you may switch from different mixing obstacles to others.
Thank you.
Other questions? Okay, so maybe then I also have a question. So so you told us how to achieve a better rate of mixing by perturbing the vector field. Have you any motivation or application in mind when you are doing this, or so why is this?
Yeah, thank you for the question, which I often get. So, yeah, okay. So the nice thing is that we are perturbing the entire velocity field, but then usually I get a question like, how would you do this in practice? How would you make the perturbation in practice? And of course, this is kind of difficult to manipulate at small scale everywhere the velocity field. So in practice, what you can imagine is you might have something like a salty fluid, and you have some kind of magnetic forcing from below, but you're kind of limited in the resolution and the type of perturbation that you could make. Or you might think about a fluid with some rods in it, and maybe the rods are doing the stirring, and you can change the motion of the rods. So yeah, this is something that I'm still kind of, I think this is a difficult problem to translate it to really an experiment that you could actually carry out in the lab, where what you want to do is realize somehow you want to turn changes you can make in the lab to changes in motions that the vector field is going to give you. So yeah, this has not stopped lots of people working on this problem, but yeah, I think this is a gap. So a gap is how do you translate this to physically realizable perturbations?
Okay, so thank you very much again. So are there any more questions?
I have a question again.
Yes.
People who study dynamical chaos, they wish to measure the level of chaos. And one of the ways to do it is the so-called Lyapunov exponents. Are you somehow controlling this, or have something to say?
Yeah, this is kind of an interesting point. So the Lyapunov exponents, they are describing the average local expansion in the phase space, and so but that can be very different to the global mixing rate. So you can have very rapidly expanding locally dynamics, but globally the dynamics might be very slowly mixing, and you kind of see that in, I mean, it's a little bit like that in this example. You see the stretching and folding is really pretty strong, but especially in this top example, the global mixing is occurring at a much slower rate. So there is a disconnect. These are two different things. So the upper node exponents and this second eigenvalue of the transfer operator, they're really measuring rather independent things.
Thank you. May I ask another question? Sorry. This perturbing of the dynamical systems may lead to change of the phase portrait, the so-called bifurcations. We have a large group in our laboratory who study bifurcations. Have you, tried to plot the bifurcation diagram or something like this in your setting?
No, I guess because usually at bifurcations you have some small number of parameters that you are changing, and here I guess I explicitly wanted to not take that path. So many of these people that I mentioned.
I saw the name of Veritrom Kidar here.
Sorry, I've lost it. Where did I? Here. Yeah. So a lot of these guys, they are doing a small number of parameters, and so in their settings they could do some kind of bifurcation analysis as well. But I guess I'm trying to explicitly avoid that by making a general perturbation in vector field space rather than a single or two parameters.
But of course, some bifurcations occur in your procedure.
Yeah. I mean, I guess I'm. One could look at the direction. So having found the direction you want to perturb in, you could proceed along that direction and look at what bifurcations occur along that direction. So yeah, you could in principle do a bifurcation analysis along the direction that you have identified as the optimal direction to perturb in. Yeah, that's also interesting. Thank you. Lots of nice questions.
Okay, so thank you very much for the very nice talk, and I think then we have 2 minutes break and